Hello everybody, I'm Alexy Khrabrov, the organizer of SF Spark and Friends, and here we are on location at Chartboost, and we have a very special meetup tonight. It's called Open Genomics, Scala and Spark for Good, how open source developers can help in genomics research and cancer research. And it's a very important topic coming out in personalized medicine. We have two great talks today. From AMP Lab in Berkeley and from Driver Genomics. And here with us we have Frank Nothaft, who is a PhD candidate at AMP Lab at Berkeley. Hello, Frank. It's great to have you.
Great to be here.
So I think Adam and Spark, so Adam is the project from AMP Lab, is really well known by this point in time in the community, and so you're one of the folks directly working on this, so maybe you can tell us a little bit about that project.
Sure. So, we've been working on the Atom project for about 2.5 years right now. And the Atom project is an attempt to use the Spark and the Hadoop stack to try to process genomic data in a faster, easier to work with way. Mm-hmm. So, when we started looking at the problem, most of the tools that are out there in genomics right now are focused on a single node, and they're based heavily around some of the legacy file formats and legacy technologies that were very common when the next generation sequencing era really started getting kicked off, 2006, 2008. Since then, one of the big realizations that we had is actually this huge growth in genomic sequencing has really paralleled how, the rise of all these high performance analytic technologies came up in the in this big data space. Mm-hmm. So we saw a very good opportunity to go ahead and take some of the tools that were coming out on the scene, whether it's a tool like Spark, a file format like Parquet, a data serialization method like Avro, to just go ahead and make it easier to process large amounts of genomic data at a high rate of speed. Mm-hmm. So over the past 2 years, what we've been working on is trying to essentially replicate and improve on some of the current standard practice in genomics. So we've been trying to tackle some of the big problems that people have in the data management side of genomics, mm-hmm. Whether it's making sure that the data can be easily processed by a wide variety of tools, can be easily accessed, queried. One of the big problems that we've run into is that the legacy tools aren't very easy for people to run ad hoc queries against. So there's kind of this meme where if I'm going to run some ad hoc genomic experiment, I'm going to be doing this through command line tools like awk, grep, sed, so on and so forth. That's all right if you just want to look at a single person's genome, but when I'm scaling up to tens to hundreds, thousands of genomes, it just doesn't work well. So we've been working heavily on these pipelines. We're starting to focus more on the ad hoc, kind of the data science side of genomics. So we're pretty excited about where the technology is heading.
So this is interesting you mentioned sed and awk, right? Because I think 10 years ago, in previous years, we had these books coming out from O'Reilly and other publishers, Perl for bioinformatics, Python for bioinformatics, right? So it's kind of interesting. Maybe you can explain to kind of folks who are not familiar with specific technologies why Spark is a better vehicle for these kind of problems than sed and awk and Perl and Python.
Sure. Well, there's a few things, and the big first thing is if you look at the computational patterns that are in play. You have these tasks that are processing very large amounts of data. A single human genome in non-summarized in its just rawest form is about 200 gigabytes of data. Mm-hmm. When you start talking about these large file sizes, moving to a parallel system like Spark, that's really optimized for making optimal use of data locality, mm-hmm. High performance file systems. It's just it's a good step in the right direction. Additionally, one of the big reasons that we think Spark is a good fit for this, less so than legacy Hadoop is that a lot of these pipelines rely heavily on iteration. Mm-hmm. They may be a lot of the algorithms that people are running are similar to machine learning algorithms. You have lots of iterative algorithms, mm-hmm. but additionally, even the non-machine learning like algorithms tend to rely on a long pipeline that is job cascaded after job, cascaded after job.
Like string matching, right, and things like that.
Exactly, and it's that's a good fit for Spark. Additionally, one of the big advantages that we see over a lot of these legacy tools where, people are going ahead and they're piping tools through command lines and so on and so forth, is we've taken an approach that focuses a lot on having a schema as the descriptor of data instead of some binary or text-based format. And there's a few advantages to this. Right now, I can take this ad hoc query that I'm running on the command line, and I can go ahead and I can move it to a tool like Spark SQL or Impala, and I can run my data analysis queries in that tool in a higher level language than someone who's just piping things around on the command line.
Yes. And that actually reminds me, right, one of the themes of the upcoming Scala by the Bay conference, we call it no ETL, right? And ETL basically means you dump something into text and then you parse, so you lose the schema, you lose the typing information. So it's interesting that you're focusing the same advantage that you're keeping the information in between the stages.
Yeah, definitely.
And I know that you're using Avro and Parquet for this purpose.
Exactly, and we've been doing a lot of optimizations recently to try to improve our performance, with those technologies. There's a variety of, we get very good performance right now, but we found a couple of, actually like low-hanging fruit that allow us to optimize things even further.
Interesting. I hope to hear more about it. So one question that a lot of developers in this community ask, especially we see huge enthusiasm about tonight's event. We have more than 200 people signed up. People come from different companies, and the first reaction when we share this at night, showing this shared at other companies, is basically how we can help, right? So people even not in biotech space want to, for instance, enable their open source developers to work on this, right? They want to contribute, and obviously this is not as easy as kind of picking up a how-to for a Linux project, right? You need to learn more. So since you've been dealing with this area for a long time, can you summarize what is a good way for somebody who is open source developer, who is enthusiastic about it, but doesn't know much biology, right? What's a good way to learn more about the space, about the problem, and maybe kind of understand what algorithms need improvement, how they can help with the whole area?
Sure. That's a great question, and I know that's something that I found kind of difficult when I came into the field myself. So we've been trying to do some work in the Atom project to try to reach out, do more developer-facing documentation. One of my colleagues, Uri Losterson from Cloudera, had a chapter in a recent O'Reilly book on how to use Spark to do data science. He had a chapter talking about basic introduction to genomics and showing how this maps into a Spark-based pipeline. My colleague Matt Massey has a similar chapter coming out in a Hadoop-focused book. So we're working hard to try to put together some examples there. We're trying to put together a tutorial article as well. Otherwise, I think part of the problem can just start with understanding where the data is coming from and what some of the big challenges are. It's kind of daunting. The literature in the field is it's vast and wide, but one of the things that is good in biology is that we do have a very large collection of review articles. So these are articles that try to give more background on specific topics, specific analysis needs, that try to give the history of the problem and current approaches to solve it. So there's a variety of good articles there that are great for people who are coming up in the field. The other thing, and I think one of the areas that's very good, and actually an area that I kind of eased myself in, is that even if you're a computational person who doesn't yet understand the algorithms, a lot of how you can get started may be around optimizing some of the performance. For a lot of us, if you come from the data engineering side, you're used to running big Hadoop pipelines. You understand, how to tweak the performance and optimize the performance of these large, long-running, analytics jobs. And we've actually had several people who've gotten into the project by saying, hey, I kind of understand what this algorithm's doing, kind of vaguely. I'm going to measure its performance, try to make it a bit faster, And then, 3 months later, they wind up, really understanding how everything works in the system, what some of these important algorithms are, what the data types look like. So, it's a bit more computationally friendly. It's the type of thing you put your computer hat on, you start to make some, modifications to the code base to see if you can improve performance, and just by doing that, you can understand a lot about what's going on in the system.
Got it. So you basically start kind of knowing, using your skills in optimization, and then kind of expand more into the domain space. And that actually brings me to the question: what got interested you in, like, why you got into this field, and what kind of people, I would say, by generalization, can be interested in the biology problems?
Sure. Well, the big thing for me that got me excited about it is just it's this opportunity to really apply computational technologies to something that's a greater social good. That's what something that really got me inspired about it. I was looking for a way to really start playing around more with the big data stack. Came across this application domain, dived in, and haven't regretted it since. I think one of the great things about this kind of quantitative area of biology is that it's somewhere where a wide variety of people can come in and start working on problems. If you're a strong developer, we always need people who can go through and put together these algorithms, get them running fast, processing large amounts of data. If you're someone who has more of an analytical mind, more of an algorithms background, a lot of these algorithms that we're using in genomics are fundamentally, they're based on really core theoretical computer science. Maybe they're based on graph theoretical algorithms. You're doing some sort of string edit distance comparison. So that's another area. And then fundamentally, a lot of what we're doing is some form of statistical inference.
Yes.
So, we have this huge community in the Bay Area that's, developed this huge data science community. A lot of that is some form of, statistical inference, machine learning, and a lot of those skills naturally map very well to the problems that people are tackling in biology.
A data engineer, of course, right? So like all these things together.
Exactly.
Interesting. So, I'll probably wrap up by kind of hypothesizing. So let's say, personalized medicine obviously is gaining momentum. Let's say magically you have 1,000 developers at your disposal, all right? You have a building of top-level Scala and Spark developers who are, eager to help, right? And through the community effort, effectively, you have, part-time, you have some of the spare time. Instead of building another pet store on Ruby on Rails, they will help with Adam, right? And hopefully we'll get enough tutorials, enough resources to explain them, basically, the space, right? So you can put them on any tasks in this pipeline, right? So what would you do with this force? Where would you direct the effort? Where would you call the attention? What should they do?
Sure, that's a really interesting question, and one that I've been thinking about a lot recently. And what's kind of interesting is one of the big problems in genomics is a problem that anybody who works in a organization that has a big data lake or big data silos can relate to. And it's dealing with discovering large data sets and figuring out how to aggregate across those data sets well. A lot of the algorithms that we've been working on in the first 2 years of Adam have been focused on some of these initial discoveries that you want to make. You want to detect, how is your genome and my genome different?
Right.
So we've spent a lot of time in the last 2 years working on that. But in the future, what I'd like to see, more focus on is saying, okay, well, now that I understand why, how your genome and my genome are different, how does that influence, how the biology of our bodies works differently? Why does that influence some of my personal disease risk factors? How does it change what traits the two of us have? And all of this fundamentally is a statistical process that depends on having very large data sets. Especially if you look, there are some studies that have looked at, for example, schizophrenia, autism, Alzheimer's disease. There, if you're able to go ahead and look at, not 10 people's genomes, not 100 people's genomes, but 10,000 people's genomes, you have a much better understanding of what genomic links there are between that disease, essentially what links there are between that disease and the genomics. But one of the problems right now is even though we can build these algorithms to do these sorts of aggregations, it's actually very difficult to manage the data sharing, and a lot of this is for good reason. Fundamentally, whenever you're collecting information about someone's genome or someone's health status, someone's familial health, there's a lot of important personally identifiable information there.
Yes.
So we see a lot of challenges coming up in, kind of one in the area of, if I'm a doctor, if I'm some clinician, how can I discover who else has a cohort of Alzheimer's patients? Who else has looked at people with acute myeloid leukemia?
Mm-hmm.
But then once they've gone ahead and done that, and that's fundamentally a metadata search problem. It's a search and indexing problem, something that us computational people have thought a very long time about.
Mm-hmm.
It gets into this question of how can we do analytics in a way that manages these privacy concerns.
Right.
And I think it's an interesting problem. I don't think it's been looked at a ton in the analytics space, but I think it's a very natural extension on top of what people have been doing in the analytics space.
Yes, I think that, yeah, so privacy preserving data mining, I think it's a whole field, right? And obviously, with the volume of data, it will need to improve, especially as algorithms get better and better. That reminds me, I probably will add one more question to this. So you mentioned basically, there are these tasks and they involve multiple bodies. Obviously, privacy is governmental regulation, but the database are maintained by consortium. So, for those who are not in the field, can you maybe briefly outline kind of what are the other forces, what are the key groups, and we can supply the links to this video, right? But what are the key bodies in the academia? What are the key bodies in kind of big data, genomics that you think it's useful for folks to follow, to learn more about, right? Because there is a lot of centers where this knowledge is being kept, a lot of different organizations and companies which basically want to solve these problems.
Sure. Well, there's a variety of groups out there. There's obviously our kind of large open source group.
Yes.
There's also a similar open source effort that's coming out of the Genomics England project. This is a project to go ahead and sequence 100,000 people in the UK.
Mm-hmm.
They're developing a similar open source stack called OpenCB. Mm-hmm. So that's another resource for people to look at. There's a variety of other places. It's kind of hard to say a single place, but there's a lot of interesting discussion on the privacy and data sharing side coming out of the Global Alliance for Genomics and Health.
Yes.
That's a big one, and then one of the wonderful things with the field of genomics is that there's so many great people doing such valuable work that it's kind of hard to point to little centers of excellence.
Yes.
But I know there's a burgeoning community that's really kind of coming up in the open source and scalable tools for genomics world. So I think you'll start to see more projects starting to come up to speed over the next year.
Okay, so I'm looking forward, and for you guys, we'll have more resources at the new community site called opengenomics.io, which we're putting together to aggregate this resource. We'll have more links, and we'll definitely follow AmpLab's progress, and hope to have Frank's research linked from there, past, present, and future. And we're looking forward to your talk today.
Great. Well, thank you for having me.
Thanks, Frank.